Okay, now let's talk about radiation from an infinite plate. The reason we looked at the mechanics of plate vibration is because we're interested in how plates vibrate and what they do and so on. So now we're coming to our main goal. This is the radiation problem from a plate. Now, if you recollect, the plate equation impedance has, let me just put it on the corner here. Okay. Any system at the end follows the forcing. Okay. Whatever is forcing that system, it's going to respond to that forcing function. Okay. In this case, forcing function is, we express for our purposes in a wave number as well as frequency domain. Okay. So if you take a single wave number and single frequency, then you say, okay, we have and you're familiar with these expressions, okay? So we're forcing the system with one wave number. And this is the forcing, not the free bending wave. Remember, that's KB. That depends, that's driven by this, okay? And a frequency that's involved. So keeping that in mind, we say, fine, our plate I'll exaggerate the shape. Okay, this is the displacement of the plate. And the bending wavelength of the plate, that's vibrating. And in this case, rather than displacement, well, this is velocity. Okay, we say the velocity is expressed as v0 e to the I k bx. This is the bending wave number. Z is into the fluid medium, and what we have here is sound pressure that's radiated from the plate, and lambda being the let me make clear, this is not normal, but theta. Okay, lambda is the wavelength of the sound in the air. Okay, so we say plate is in XY plane, but the waves are in one dimension in the extraction, and plate has a harmonic velocity, And you can see from the geometric relationship the bending wave and the wavelength, bending wavelength and the wavelength of sound in air have a geometric relationship. Now the radiation field. The radiation field from the plate can be expressed as an amplitude. What is the spatial dependence? If you look at this shape, what does it depend on? The sound pressure. What are the spatial dependencies? How would you write it? Remember, whenever we solve these wave equations from one medium to next, between two media, etc., we write a general expression for the pressure. What would you write here? Come on. Say again? Yes, an outgoing wave.
Similar to the harmonic.
Okay, tell me what to write. Yeah. Okay, tell me what to write. E to the
KZ Z plus K X.
Excellent. And harmonic time. Right? That's all it has to be for a single wavelength. So that would be the expression for sound pressure. Well, how do we find these various quantities and the amplitude? Okay. What would that be? Who can help? What do we know? What is causing sound? What's causing the sound pressure here? Impedance is not active. Impedance is just a property, something else. Wake up, class. What's causing it? Go ahead. Yeah, vibration. Okay, what do we know? How do we use the vibration? What do we know about the vibration of the plate? John? Eta dot. Okay, what is that? In your words, what is eta dot? Velocity. Plate velocity, right? Okay, so we know plate velocity, we talk about continuity. We're really talking about a boundary condition here. Okay? That's the source that's representing this. And how would we do that? What is the boundary condition here? How do we go about using what? What's the next step? How do you use the plate impedance? Right. See, you mentioned it earlier, the continuity. The normal velocity of the plate surface must be equal to the normal velocity of the particle. Because, excuse me, that's what's pushing the sound particles, the air particles or fluid particles, okay? And that is the usual continuity equation. So the boundary condition is then rho del u z over del t is equal to what? The pressure. Change of pressure in the z direction. So you have a general expression for pressure, and of course this is at z equals 0, both cases, because this is true only on the surface. And since uz Okay, an interesting situation comes up now, right? Because the plate expression has the bending wave in extraction in terms of bending wavelength, whereas we don't know. There's an X dependence in terms of wavelength for the sound pressure. So for this equality to take place, okay, we need to have, number one, KB must be equal to KX. That's the forcing function. And then the amplitude is determined by rho omega kz. Okay? This is the amplitude. But there's something else that needs to happen here. And that is the pressure expression must satisfy the wave equation. Always. Okay? And the wave equation, at least in this case, is, yes, it's a mistake here. Now, if we substitute from the expression for pressure in here to make sure that it satisfies it, now we have P0 for Kx Now, of course, K is the wave number in the fluid medium. And when you consider its components, it's kx squared plus kz squared. Okay? In our case, kx is equal to, we already determined, the plate bending wave number. Now, what does this do for us? Now we have an expression for stop here for a second and let's review what we're doing, because this is a critical element. Okay. Let me just review and just pay close attention, and if you do not understand something, because some things that you learn are the most fundamental. If you don't learn it well, everything else becomes difficult later on. So this is an issue that's important, and it will become clear in just a second. What we're trying to do now is we're assuming that there is a plate that has this sinusoidal wave shape, okay? The wave is traveling in a sinusoidal wave. And how does it radiate? What does it mean? Of course, we don't know. This could be an arbitrary wavelength, wave number, frequency. So we're trying to find out some relationships, okay? So you have this sinusoidal shape, which is represented by the real part of this exponential. Okay, no problem. All right. As each individual element on this plate moves, okay, there's a phase relationship, obviously, between them. Pressure is moved up and down, okay? And collectively, they radiate sound. And we express that radiation in z and x directions, because it has z and x dependence, okay? It's just a general pressure expression. There's no mystery on this. Everybody is okay with this? And then the next thing we say is, okay, because this is caused by the vibration, we need to find out what the continuity or the boundary condition, how does it affect it? And boundary condition, we say, is acceleration of the particle, okay, on the surface is equal to the pressure change with respect to space, spatial variation of the pressure. But this acceleration is also the acceleration of the plate. That's the continuity. And when we apply that, we find two things, okay? One is, on the pressure side, of course, it comes from this expression here, del P over del Z. We have x dependence as k sub x. On the velocity side, we already know it's a bending wave. So KB must be equal to Kx. What does this say to us? What it says to us is, in this pressure expression, as you see it, this x dependence must follow the forcing function, must follow the bending wave of the plate, because nothing else is causing it. It must have the same x dependence, because it's a forcing function. Okay? Any doubts, any problems with that? No. Good. But we don't know what the z dependence is. We know this is a must. Okay. Well, the next thing we know is pressure expression, the same thing, must follow the wave equation. And if you write the wave equation, as you know, the the second derivative, this would be kx, but we have already figured out kx is equal to kb. We come up with this relationship. And this relationship essentially gives us the same thing. Okay? And from here, now we have what kz must be. Kz must be equal to this. Now you have, you're seeing something strange, okay? Now we're looking at, kb versus k. If kb is larger than k, then this is imaginary. What does it mean if it's imaginary? It decays, right? If this is imaginary, then you have a pressure e to the I kzz, and if kz is an imaginary, purely imaginary number, what you would have then is an exponential decay in z direction, okay? You have an exponential decay, and this is what we would call an evanescent wave. Okay, now we'll get to the physics of that in a minute. Go ahead, finish your notes. Of course, that would be only true if kb is larger than k. Okay. If we look at back here, if you look at back here, okay, the plate is still vibrating, bending waves are traveling, okay, but in this case, the radiated sound amplitude kind of goes like this, okay? As you get away from the surface, pressure is negligible. And what does happen is energy is exchanged back and forth, and then this becomes what we would call a reactive field, okay? There's no resistive field. Resistive field would be sending the acoustic energy into the far field radiation. But this is reactive. Energy is exchanged between the plate and the fluid back and forth. It's just imaginary pressure. Now, let's see if we can relate some of these a little bit. We're saying if kb is larger than k, we'll usually say no radiation. Okay, let's examine this just for a moment. What's the wave number? Kb is equal to 2 pi over lambda b. Okay, and we're saying if this is larger than 2 pi over lambda, which is equal to k. And this amounts to lambda being larger than lambda b. Okay? If you look at this expression, okay, there is no real angle theta if lambda is larger than lambda b. Okay? So they're all very consistent. There is no real angle, there's no radiation angle. It just does not happen. So this is the fundamental aspect of radiation from bending waves. Okay? The bending wavelength must be larger than the wavelength in the air, which is always constant, which is always the same corresponding to a given frequency. Okay, so if we, let's see now, let me clean the board a little bit. Taking all of these and expressing the sound pressure. This is the pressure amplitude that we obtained a moment ago. We can also say, express this in terms of pressure amplitude, velocity amplitude, and we would call this the radiation impedance of the plate. Okay? All right, so from here then we have Z bending waves. Of course, then it follows what the sound pressure would be. Okay, that's one expression. That's the pressure expression for radiation from a plate. And we can write this in terms of speeds of sound. As always, lambda KB is lambda B. Okay. Pressure reaches yet another expression. Oh, there's something missing here. Okay, so let's radiation impedance once again. Okay. Let's consider the case where the bending wave speed is supersonic, meaning it's faster than the speed of sound in air. That makes the wavelength of the plate longer than the wavelength of the sound in the air. And that's when radiation takes place, and that's when the impedance is real. Now, this is the impedance, rho c over cosine theta. Have you seen anything like it before? This is radiation impedance. I'm sorry, say again. Oblique incidence, okay. Basically, rho c is the specific acoustic impedance of a plane wave, okay? And you have seen that before. And it's modified by 1 over cosine theta. And that's what it shows, okay? That's exactly it, 1 over cosine theta. Now, what is cosine theta? This being sine theta, okay? So that would be the angle, cosine of this angle, okay? So there's a chance cosine theta can be 1 or 0 or anything in between. Now it will become important what it means for cosine theta to be 0, because now you're talking about radiation with an infinite amplitude, okay? Of course, that's not true. That's never the case because of damping and other issues. But what it does say is at a particular angle, and that particular angle can be only determined by bending wave speed, and the bending wave speed depends on frequency. So at certain frequencies, radiation amplitude will be the maximum, like again, spatial resonance. Okay? This morning, you look very tired. Is it 8:30? Or is it the exam results? Maybe a combination of both? Okay. All right.
Can I ask something?
Yes.
Oh, we are still in vacuum?
Yeah. No, we can't be, because we're radiating sound.
But radiation doesn't leave it.
Correct. It's radiating, but we're assuming that the effect of radiation on the plate vibration is negligible. That's the third topic that we're going to cover. What happens when it is not negligible? Okay? This is for many applications of a metal plate in air. It's acceptable. Not all, but for many applications. Like thick plate in air, the pressure doesn't really affect it very much, except under certain circumstances. But in fluid, like in water, for example, definitely you have to take into account. Or for very high pressures, you have to take it into account. That's the next step. But we can't say it's in vacuum. Then there's no pressure. Okay. What else? Any other? Okay. One thing that we want to define here is just very quickly a radiation efficiency. This is this is a term that one comes across in acoustics quite a bit, and here what we're doing here is we're comparing radiation with when lambda would be infinite, meaning if you remember that flat surface case when it radiates, okay? And the radiation efficiency of bending waves is equal to 1 over cosine theta, and that actually is also expressed as k square, kb square difference square root, but this is... So if I were to plot that, what do you think would come out of that if you were to plot this expression? Z over rho C. Is a function of FFB, or speed of sound for that matter. We'll drive this, this will become a bit more clear, but this is this expression, okay? The same expression. We see that at low frequencies, this is a mass impedance. And at high frequencies, it becomes real, and it is a radiation impedance. In other words, there's a particular frequency, which we'll explain in just a second, where above which radiation is real and sound is radiated. And it is at the same frequency where the radiation is at its highest peak. Are you warm? Are you hot? No, you're okay? All right, good. Now, what we want to do is consider the third item, that is the influence of fluid, okay, on the plate. As I mentioned even last time that when you have a plate that's radiating, okay, this pressure field here also acts on it, okay? So you have an expression for the plate vibration. That's forced. Now you will have pressure that's also acting on it, but pressure is xzt, right? At, of course, evaluated at z0 on the surface. So this is what we're going to do now, see how we can formulate it and what other critical parameters that it brings us. And let's call this the equation of motion. Of a plate in an acoustic medium. An acoustic medium. And if we write the transformed equations that we used a moment ago, okay, z, in the z direction there is no variation because we evaluate the pressure on the surface. Now, this is called sometimes the fluid loading effect, fluid loading, okay, or acoustic loading, the pressure that comes back to act on the system. And different way to express it would be plate impedance and radiation impedance. Okay? Now, please tell me if this is not clear to you, what we have done now. Is it clear? Okay. And no problems there. All right. So what we do is you can now see that the plate motion would, against the force is resisted by not only the mechanical impedance, but also the radiation impedance. See how nicely and in a compact way one can represent that. Okay? And just to remind ourselves, the plate impedance with some losses was given as such. Kx is k sine theta. These we have written before. I'm just writing them for don't forget the fourth power, it's very important. Okay, so this is the expression. We know the expression for plate impedance. We just drive the expression for radiation impedance. So for any given forcing, we should be able to obtain the response of the plate. Now, there are a couple of conditions that are important to us. One is called the coincidence condition. And coincidence frequency. Okay. Remember we said when Kx is equal to Kb. Who can tell me in words what that means? In words, Kx equals Kb.
Rebounding.
Mm-hmm.
Plate is equal to force vibration. Wave number.
Force wave number. Say again? Spatial resonance, right? Okay, good. Thank you. And that's the condition. We know that there's a frequency dependence involved in these. We said Kx is equal to k times sine theta. So let's write the equivalent value on the left-hand side. And bending wave also has, let's see now. Okay? If we put the equivalent values, what this gives us a frequency okay, to distinguish this frequency at which kx equals to kb, we call it the coincidence frequency. Okay? They coincide, their values coincide. That's the coincidence frequency. Now, one more step, sine theta. Sine theta is always equal to 1 or less than 1. Okay? Now, what that means is the maximum value of sine theta is 1, so coincidence frequency has a lower limit. And what is that lower limit? And this is what's called the critical frequency. Okay? That's called the critical frequency. Okay. These are important concepts. I'll tell you why. As simple as design, excuse me, designing windows in a building, in a high-rise, okay? If you are on the 10th floor, sound is coming to you at an angle, and you want to be able to select the thickness on the window glass such that you avoid some of these frequencies and this condition. Because at that frequency, sound is going to come straight through at the highest transmission. We haven't done transmission, but we will do so in a few minutes. So these are actually important numbers from a design point of view. When you're designing something, one of the things you do is, okay, if I select, because see, B here involves the thickness. Remember how important thickness was? B is E times H cubed. Okay, so you want to be able to make your selections accordingly, whether it's a window, wall, plates, shells, structures, and so on. So they are important parameters just to keep in mind, and also to understand exactly what they mean. Now, if there is such a relationship and an angle is involved, of course, we must have a coincidence angle too. So let me just define what coincidence angle is. Because once we understand how a plate-like structure is responding to force and mechanical force and radiating, the next thing will be, how does it respond to a sound wave, just like a fluid medium? And what does it radiate to the other side? Transmission, transmitted sound. And what does it not radiate to the other side? These will be important. So the next is coincidence frequency. And coincidence angle. The relationship, of course, between coincidence and the critical frequencies are through the angle itself. So what we call critical or coincidence angle is the ratio of the frequencies. Okay, critical frequency we define it also in terms of when the bending wave of the plate is equal to the speed of sound. And from here I can write this as it's the critical frequency. Okay. Any questions on these? These are, if you look at this simplified relationship, Cp, we defined it earlier as Young's modulus divided by the density of the plate material divided by 1 minus Poisson's ratio squared. So it's a plate-specific number, speed of speed of sound in plate material, speed of sound in fluid, water, air, whatever it might be. And then if you know both, you can get this critical frequency as a function of plate thickness. Okay, just a simple, nice way of using or finding out what the critical frequency is. Any questions about any of these? What are we going to do with these? Yes, go ahead.
Yes, about the usage of this frequency, we compare with the ultrasounds, like that's what human can hear.
No, not. Tell me more. I'm not quite sure I follow the question.
Okay, then this frequency, we compare with this, the frequencies that human can hear, so that transmission of the sound, for example, from window.
Well, first of all, you use the word ultrasonic also, or ultrasound. Ultrasound, by definition, is beyond human hearing. Okay, that's a different. It has medical applications, some other things, but in general, why we try to learn these is we're trying to understand so far how metals or how plane surfaces vibrate and radiate sound. Okay. Next thing we'll do is when you have a planar structure, okay, how does sound that comes from one side transmits to the other side? Where do we need to learn these? A number of different things. Again, as I said, from a factory, for instance, in very large and crowded factories when they have punch presses, I mean, we're talking about very large objects. As the punch comes down, they vibrate the metal plates all around it, and they radiate incredible amount of sound. That's an industrial application of one sort. Or automobiles. In an automobile, the lower panels, side panels, as you're driving, either through the structure, the wheels on the road, they get, the vibration gets transmitted through the, and then they vibrate. I mean, that's another application. or airplanes, okay, the fuselage, the turbulence does that, or in defense-related applications, ships on surface or underwater ships, how they radiate. That's a very big application. In fact, that's been a very strong application. Rockets. As you send a satellite up, for example, even if it's not defense, but just sending satellite for to make weather measurements, the vibrations on the hull actually is transmitted to electronic components and it destroys them. So these are all very relevant to how you might want to design them so sound doesn't transmit as effectively into the interior in some of these cases. Or in other cases, you know, you're in a noisy environment, you're doing something, but you don't want sound to transmit to the other side. Okay, those are some of the common applications for these. I'm sure there's more. All right. What else? Any other questions? Do you feel you understand this number one, plate vibration, radiation from plate, and the role of loading on the plate? Okay. The role of loading, basically, it provides another load in terms of a radiation impedance. Now, what is the most interesting thing that came out of these three topics? Everybody might have a different idea, but to you individually, there's no right answer or wrong answer. Is there an interesting thing, first of all, and what is it? From your perspective, what was the most interesting? You might say, why didn't you give these to us before the lecture? On purpose. Make sure they're all correct. There might be some typing errors in them. But tell me what it is that you find intriguing, unusual. Anything? You should always think about this. When you're listening to somebody, you should come away with at least one thing. Okay, just one thing. What would it be?
It's the radiation condition.
Radiation condition. Oh, okay. Okay. Yes. What is?
For me, it's not interesting, but it's new spatial resonance.
Spatial resonance is new. That's correct. Yes. Yes.
I think the angle part is interesting because I think the pressure should attenuate, but there's no real angle for that. There should be imaginary for these.
Right. Right.
I think it's the first time we introduced damping.
Oh, in the elastic material, internal damping. Is that right? You have not seen it before?
No, in acoustics.
Oh, in acoustics, yes. Well, of course, what we did was we introduced it into the plate material. Yeah, mechanics, but not acoustic absorption, which we will do later on. Yeah, let me describe to you very quickly an experiment that will speak to this radiation business. Okay, let me just very quickly just think about a plate. This is a real experiment that my students and I had conducted some time ago, and it showed, it demonstrated some of these problems. Just a plate, actually a circular plate like this, okay? And we dropped just a spherical ball in the middle. You can imagine that you hear a clack and then ringing, ding, sounds. Now, all right, if you measure the sound, let's say here, versus, or here, versus here. When you take a look at this, you see sound like this. This is sound pressure, roughly something like this, okay? When you look at the microphone here, something like that. Okay? What does it tell you? How do you make sense? Go ahead, based on what you have learned.
It's about the speed of plate speed based
Bending.
on the frequency.
Uh-huh.
So it takes time to get sound pressure.
Yes, all of that, right. This one is the immediate, the first impulse. That plate is hit by the ball, and then almost nothing. What's happening here? Why don't we hear anything? There's literally almost nothing here. Why is that?
Can you just repeat the setup, please?
Sure. This is a round plate like this. Okay. I give it a pulse with a little steel ball bearing. Just drop it, okay? And then you make sound measurements either on the other side or just above this and then near the edge. And this is the center, this is the edge. These are the types of, actually this is even here, pressure waveforms. We say this pulse, immediately recorded, but then there is nothing for some time.
I think it might be the reflected sound from.
Reflected sound? No, there's no reflection because this was done in what's called an anechoic chamber. So sound does not reflect from the walls, etc. And the other thing is, this measurement picks up immediately, fairly soon, fairly quickly. Okay? You can actually answer this with what you have learned today in the following way. What happens is, just think about what happens here. When you're excited, how does a plate behave? Think about water, okay? Just a container, round container with water. You drop something. What do you see? Exactly, waves going out, they reach, and they start coming back. Okay? So just like in the plate equation, that's sine theta, okay? As they go out, they radiate. As they travel out, they radiate in the outward direction. Okay? That's why you don't hear anything when you're here, until they go and they start radiating back. Whereas the microphone at the corner, as soon as the waves start traveling, it picks up the radiated sound. You see what all of the equations that we had means? This is exactly what goes on in there. I should write this up because I forgot. I wasn't going to mention it, just reminded me what exactly happens in reality. Okay? It's a very nice, very simple experiment. And at first it was very puzzling. Then, of course, it became clear. And at a conference, a young man stopped me. He said, "Oh yes, I read this paper. It really helped me understand a lot." That's, of course, what you want to hear when you do these things. So this is very helpful. You understand now what it means, radiation at a particular angle and so on. Okay? And speed of sound traveling. And all of these, of course, is a combination of a number of different waves. Because when you excited with an impulse, it's not a true impulse, but short duration force, then you're exciting a number of different waves, not just one wave. And all of these have different speeds with which they travel. All right, any questions? If not, thank you, and I'll see you Tuesday. No, is it? Right, next Tuesday. Okay. Okay, thank you.